ratio is going to be approximately what? 1, right? It's going to be approximately 1. Now again, when we talk in statistics, approximately 1, well, we have to get cutoffs for what we mean. Is 1.51? Is 2 close enough to 1? So we're going to have criteria for that kind of cutoff. But it's that idea. Okay? If we have a strong signal, meaning that there's large differences among these groups, that the means are far apart from each other, that means that MS between will be large relative to MS within. And that means that our F ratio will be large. Okay? So what we're going to have to talk about today, well, we're going to talk about a variety of different things. But what we need are formulas to help us calculate our F ratio and then figure out whether this is significant or not. Okay? So that's what we're doing in Anova. Yeah?
MS within you said was made up of the error variance?
Plus error variance plus what?
MS within.
No. MS between, right? You said MS between?
MS,
Oh, MS within, yeah, it's just error variance. Yeah. Right, like people within a group, why are they all different, the scores within one particular group? Well, it's just individual differences, not because anything in particular is going on. Okay? So are there questions on that kind of basic idea? Because, right, remember what we're talking about. The question is, are these means different from each other? That is, do those three means represent different populations, or do they represent one large population? MS between and MS within are both estimates of that population variance. That's what it is that we're going for here. Okay? All right. So let us move on. We were talking about the F ratio, the F distribution, right? Because we need a distribution to determine significance. So the F distribution we talked about is positively skewed. Can't be less than 0. Why can't an F be less than 0? Yeah. Yeah. Those variances are all squared. They're all squared, so you can't have an F less than 0. Less than 1, yes, but less than 0, no. And in order to find the degrees of freedom on our chart, we need 2 sets of degrees of freedom, right? Because it's degrees of freedom for the numerator and the denominator. Because again, I never ask you to memorize formulas or not too much. It's a really good idea to know that an F ratio is MS between divided by MS within. At least in this case, it's a very useful little factoid to have at your fingertips. All right? And again, MS is another name for variance. How do I get a variance if I have a sum of squares? Yeah, I divide by degrees of freedom. So because I have these 2 variances, there's a degrees of freedom for the numerator variance and a degrees of freedom for the denominator variance. So that's what these degrees of freedom are going to be. For between, or the numerator is k minus 1, k is the number of groups. And within is going to be nt minus k, where nt is the total number of observations. The total number of observations. And again, minus k means you're taking off a degree of freedom for each group, which is typical. That's what we did with 2 groups as well. Okay, so ANOVA is essentially always one-tailed. What do we mean by that? Well, so far, right, when we had t-tests could be 1 or 2-tailed, right? With ANOVA, it's all one-tailed. Why? Because in t-tests, remember, it could be A is larger than B or B is larger than A. We could look in either direction. But in ANOVA, the difference is going to be this. Let's say this is our critical value, okay? The different tails, if you got a value that fell down here, if you got an F ratio that fell over here, in this area of the distribution means that the means are close together. Whereas if you got a value over here, right, further along, it means that the means are further apart. So that's what you're testing with an F ratio. Are the means close together or are they far apart? So that far apart is only in that right-hand tail. So you're only really looking in one tail of the distribution. So your whole alpha of 0.05 or 0.01 is in that right-hand tail. Okay? Now, I believe we're up to examples. I just have to let you know, he gives you 3 different sets of formulas for Anova. The first one we're going to do uses mean squares, and it's for equal sample sizes. The second set of formulas uses mean squares, and that's for unequal sample sizes. And then the third set of formulas uses the sum of squares approach. Okay? So we're going to walk through it. The computations, nobody, is going to have trouble with the computations, but we're going to walk through all of them. So let's take a look at this first example. This is our counseling example that we had started talking about. And the question is there a difference among these different types of therapies for treating phobia? Now look at the means. Yeah. That's okay. The number of groups. The number of groups. And when I say the number of groups, also think of it as the number of levels of the factor. Right? What's a factor? Anybody remember? What's a factor? The independent variable, right? So we could talk about levels of a factor. Like in this example, the factor is therapy type. We have 3 levels of therapy type that we're looking at. So I refer to it as 3 groups, but you can also refer to it that way. Okay? Now we look at the means. These numbers represent the increase in heart rate when exposed to the phobia-inducing stimulus. Okay? So what happened was these people all underwent whatever kind of therapy they underwent. And then they were shown the stimulus that was anxiety-producing for them, and they measured increase in heart rate. Okay? So if you're just looking at those patterns of means, any thoughts? Differences? No differences? Which is better? Which is worse? Have any thoughts on this? Yeah.
General counseling seems the worst by a long shot.
Yeah, it seems that general counseling is doing worse. It's interesting you said by a long shot, right? Because we're talking about increase in heart rate. We're not sure. Like sometimes it's really easy to see, oh, there's a 5-unit difference. That might be big. Sometimes it's not so easy to tell, right? But so, yeah, general counseling seems to do worse. And may be different from the other 2 therapy types. The other 2 therapy types don't look like they're necessarily different from each other, right? It's always useful to look at your means and see whether there's a pattern because, we do so many computations, it's really easy to make mistakes. But if you have some idea ahead of time what you might be looking at, it helps cut down the kind of errors you make. All right. So we have our means, we have our standard deviations, and we have our sample sizes. Again, this is equal sample sizes. So let's take a look at these formulas. It's actually pretty easy. All right, even though these look like a lot, they're not. M is between, that's our numerator. Look at the formula here. X bar I means the mean for each group. Minus X bar G, which means the grand mean. The grand mean, right, if I put all the groups together and I got one mean, that's the grand mean. Okay? So our big questions are going to be what's n? And then we have to find k minus 1. But that's not, none of that is difficult. So let's do that first. And again, our hypotheses, our null hypothesis is that these groups are all equal to each other. And even though I only have 3 groups here, you could do this with 4 or 5 or 10 or whatever. I do 3 because in class, 3 is as many as I really want to handle generally. Okay, so let's look at MS between. Let's write the formula down again. Question? Question?
What was the X bar G?
X bar G is the grand mean. What is the grand mean? If I put all the scores together and I got one overall mean.
Oh,
okay. All right, so the big question here is always what's n? Oh yeah, you had a question?
Will X bar G always be given to us?
No? How do you, if your sample sizes are equal, how do you figure out X bar G here? Yeah, it's the mean of the means. When we do an example with unequal sample sizes, then it's just going to be a weighted means, and you'll be able to figure that out. Okay? but let's do this one first. All right, what does n without a subscript mean? N with,
Number is small, like in one group.
yeah, it's the number in each group. The number in each group. Okay? Again, this is assuming your sample sizes are equal. So in this example, what would that be? 15, good. So now our first mean is 10 minus 7. Again, I get that grand mean. Oh, I forgot a squared sign here. Okay? The grand mean is just the mean of the means here. Or if you added up all the scores and took the overall mean. Because you're finding out, bless you, essentially you're finding out how far away your group means are from the grand mean and getting a variance, right? Because you want to know how far your means are spread apart. That's the whole point of that numerator. What's k in this example? 3, good.
Do you mean 6 minus 7, right?
Do I mean 6 minus 7? Yes, thank you. Springsteen concert last night. Make sure I'm not making mistakes, okay? All right, so that's MS between. So that's reflecting differences among our means, all right? That's the numerator of our f-test. All right, so now the next thing we need to get is MS within. And that, if your sample sizes are equal, it's simply the average of your variances. The average of your variances. You take your variances, add them up, and divide by k, which is the number of groups you've got. So in this example, one thing you have to make sure about is very often the data that's given to you are means and standard deviations. If they're standard deviations, you need to square them to use them. So I did. I gave you standard deviations, so don't forget to square them. So that's my MS within. That's the denominator of my F ratio. So to really simply do this, all I have to do is the ratio of MS between divided by MS within. Now, even without doing any calculations, you can see this is not going to be close to 1. All right? You should be able to get that really easily. That's my F ratio. Just like if I was calculating a T, and I get a T value, this is my F ratio, my F observed, you could say. Okay? Now I have to determine if this is significant. So what do I always do when I want to look for significance, when I want to test this against something else? I have to look up a critical value, because essentially what I'm doing is this. Right? I get an F of 16.33. I want to know where in this distribution it falls. Right? Assuming the null to be true, I have this distribution. Where does my result fall? Well, frankly, 16.33 is going to be like out here. All right? But let's get our F critical value first. So there's 2 sets of degrees of freedom. All right? Let's actually write them here. The degrees of freedom for the numerator, degrees of freedom between, is k minus 1. So we know that's going to be 2 degrees of freedom. And then degrees of freedom, let's put it within here, is going to be nt minus k. So what's nt for this example? 45. Yeah, 45. 45 is the total number of observations. So I have 42 degrees of freedom. very often you'll see the critical value written like this. In parentheses are the degrees of freedom 2 and 42. Okay? It always goes numerator, denominator. Yeah. Yeah, but the truth is, like, you would never write up APA results with the F critical value like this. You would write the F observed with those degrees of freedom. It's just sometimes it's easy to do this so that you note for yourself what it is you're looking up. Okay? All right. So let's look that up. Okay? And again, this is our F table. Degrees of freedom numerator across, degrees of freedom denominator down. So we go 2 and 42, and we see we don't have 42. So what are we going to go to? 40, good. All right, so 2 and 40 is 3.23. 3.23. So that means this is my critical value, 3.23. It cuts off an area of 0.05. Of 0.05. Okay, so again, where is my F observed or my F calculated? Off the chart, off the chart. It's over here somewhere, 16 compared to 3, all right? So do I reject or do I fail to reject? I reject, which tells me what here in this example? I reject the null. Yeah?
That the three groups are from different populations.
Yeah, you could say it that way. By the way, what's my alternative here? Yeah, you don't write that because there are a lot of different ways that they could not be equal to each other. Okay? So when you get to Anova, this might be our null hypothesis. The alternative is that the null is not true. Because there are too many possibilities for what it could be. It could be that one group is different from the other two. It could be that all three are different from each other. You know, so you're not going to write out all the possibilities. So all you do is write that the alternative is not true. Yeah?
So then this Anova doesn't tell you where the first.
Very good. Hang on to that thought for 1 minute, okay? Right? So we're saying that these groups, that this is not, we reject this, so we're left with the idea that the null is not true, meaning that there is a difference among the groups. The problem, as he pointed out so clearly, we don't know where it is. Okay? This is the basic problem once you've gotten to Anova, all right? Once you've gotten to Anova, if you get a significant difference, a significant result, you have to do further testing. You always have to do further testing if you get a significant result. If this was not significant, if we said there was no difference here, you would be done. But if you find a significant result, you have to follow it up with other tests to see where the difference is. Anova tells you there is a difference, doesn't tell you where. Doesn't tell you where. You might have a good guess as to where it is, but you have to do the tests. Okay? Questions? Questions where any of this come from? Yeah.
What would the conclusion be to say?
So here the conclusion would be that we found a significant difference among the means. And you'd have to leave it at that until you followed it up. All right? Any other questions on this particular setup? Yeah. It's okay. (16.33) in this case, with a p less than 0.05. Yeah. Okay? All right, good. So I've mentioned this before. Let's see if there's anything else that we want to talk about in this. Interpreting the F ratio. So I've said, right, what is the variability in the denominator? What is it made of? What does it consist of? Individual differences, errors in measurement, right? Sometimes we just don't measure things quite as accurately as when we measure other things. Fluctuations in the conditions under which subjects are measured, right? You guys have all been to different classrooms on NYU campus. You can be freezing in one room and boiling in another room, and so conditions vary, and that can affect your testing. So all of this variability is, we've used this term before, unexplained. unexplained. We don't know why there are these differences. We might have our guesses, but it's unexplained variability. It's also called error variance. Error variance. So one thing that's useful to know is MS within is referred to, sometimes it's referred to as MS error, but that denominator of the F ratio is usually referred to as the error term. The error term. And the reason that this is vaguely interesting is because in this F ratio, so the error term is MS within. When we get to different types of ANOVA, that's not always the case. But it's the denominator of your F. So very often people ask when they get to higher level ANOVAs is, what's your error term? What's your error term? Becomes a big question. Okay? And the numerator variability, right? So it's a product of experimental manipulation or pre-existing groups, right? If there's a difference, and that would be treatment effect, plus also some noise. If the null hypothesis is true, there is no treatment effect. There's no signal. There's no difference in means. Okay? If the null is not true, we expect the F to be larger than 1. Again, how much larger? We have to set criteria for that. Okay. Now, just to remind ourselves, there are a couple advantages to ANOVA. One, I don't know if you remember this from the first class. I said I would say it, and then we'll talk about it again when we get to chapter 13. But what's the advantage? There's one major advantage of doing an ANOVA as opposed to doing multiple t-tests. Anybody remember what that might be? Yeah. It's not degrees of freedom. Or to ask a different way, yeah. Yeah, that's one way of saying that, sort of. What's the problem of doing multiple t-tests? Yeah, we inflate our type 1 error rate. Okay? When we do ANOVA, you'll notice we're doing everything at one shot. So we're not doing these multiple tests. We're going to get to multiple tests, but then you have to make adjustments in your alpha level to make up for it. Okay? So that's one advantage. The other advantage of ANOVA is that if you were doing t-tests, so you'd be comparing 1 and 2, and 1 and 3, and 2 and 3, right? Those would be your 3 comparisons. But sometimes those differences are not significant, but there might be a more complex difference that is, and ANOVA can pick up on that. For example, what if none of the groups are actually different from each other, but the average of 2 and 3 is different from 1? Okay? That's something that might be picked up in ANOVA that you're not going to get with these individual t-tests. All right? That's a complex comparison, which we'll talk about in the next chapter. All right, so those are the major advantages of doing ANOVA. And so it's a very good technique for it. Okay, let's get to the formulas for unequal sample sizes. See how they're different. And in this example, we are looking at whether there are differences in job satisfaction among different departments in a university. Bless you. So we have these 3 departments: social sciences, natural sciences, and humanities. And those means are ratings of job satisfaction. Okay? What do you think here? Differences? No differences? Maybe, but not necessarily and not so much. Okay, so we have to see. Now again, I've given you the means and I've given you the standard deviations. I've given you another value there, t, which you're not going to use for these formulas, but you'll use for the next set of formulas. So let's talk about what it is. T is actually the sum of x. The sum of x. So t for an individual group like 48, that's the sum of x for the social sciences. 33 is the sum of x for the natural sciences, and 25 is the sum of x for humanities. Okay? But in the context of his formulas, he calls it t. He calls it t. So we'll get back to it when we do the other set of formulas. We're not going to use it yet. I have x bar g is 7.571. Where am I going to get that from? Well, because my sample sizes are unequal, you see, right? 6, 4, and 4. I have to make adjustments in the mean. So here's the formula we're going to use for adjusting the mean. It has to be a weighted average, right? A weighted average. So let's actually do all these computations. So let's do MS between first. We started out that way before. You can start off whatever way is easiest. It doesn't matter. Notice how this is slightly different from the other formula. And by the way, even though he writes it as k minus 1, you could just as easily write it as degrees of freedom between. That's what it is. Okay? So n sub I means what? If little n without a subscript is the number in each group, assuming the sample sizes are equal, what does n sub I mean? You have to do this. You have to do the sample size for each group. So look, right? So for the first group is 6 times, the first mean is 8, minus this 7.571. Plus 4 times that mean. And again, this just happens to have the same k, because it's 3 groups. So what is this going to be? That's my MS between. Let me show you where that mean comes from, just in case you're not sure. Right? I have to take the n for each group and multiply it by the mean for each group. And what's NT for this example? 14, yeah. Okay. Anybody have any questions where these numbers came from? All right, so let's get MS within. So MS within it's still the same. It's going to be some kind of summation of or an average of the variances. But it has to be a weighted average now because we have unequal sample sizes. Oh, I don't want to write this out like this, sorry. I just want to write it in one shot. To make it more general. Right? You have to do it for each group. And again, here I gave you standard deviations. Just be careful. Sometimes you get standard deviations, sometimes you get variances. Know when you have to square or not. So we know NT is 14 and K is 3. Yeah. Total. Like which t are you talking about?
Oh, I'm sorry, the T for in the table for different numbers.
Okay, as I mentioned before, it's sum of x.
Oh,
Okay, we'll get to that. We're not using it in this set of formulas. We're going to use it in the next set. Okay? All right? Okay, so now if I get my F ratio, this is going to be much closer, eh? Got it? All right, so now I have to get an F critical value. And the F critical value is with how many degrees of freedom? 2 and, right? Remember, you need 2 sets of degrees of freedom. Yeah, 11, right? How do you get 11? Right. NT minus K, your total number of observations minus the number of groups. So we had 14 observations minus 3 groups is 11. Okay, so let's take a look at this. 2 and 11 degrees of freedom. So the critical value is 3.98. So what's our decision here? Failed to reject. We don't see any differences in job satisfaction as a function of department. All right, now part of that might be, can you think why that might be if there really is a difference? Yeah. There's an amount of noise, yes, there's an amount of noise, but also we had really small sample sizes, right? 6, 4, and 4. All right, not very big. Okay? But we don't know. There could be differences, there could not be differences. We don't know. From our data, it indicates there are no differences. All right? Questions? Okay, good. Good. All right. Last set of formulas. The other 2 are just like variations of each other. Now, so those used mean squares. And the advantage of using mean squares, well, first of all, it was actually pretty easy. We also could see, although we did it last week, so I don't know if you remember, how you get from a t-test formula to an F, right? We got to the variances through that formula. So it was kind of easy to see what was going on. Also, if you were trying to recreate things from a journal article, then if all you have are means and standard deviations and sample sizes, then it's really easy to do that. So that's fine. However, that's not typically how it's taught in most stat classes. Typically, what the books use is what they call the sum of squares approach. The sum of squares approach. Because, well, for a couple of reasons. One of the major reasons that they use the sum of squares approach is because what we're really doing is we're taking a sum of squares total and we're dividing that up. It points out that maybe we should call this analysis of sum of squares more than analysis of variance. But this is what's going on. Sum of squares total, right? SS total. If you remember, in our basic average sum of squares formula, what was it? What minus what? You know, just from the very beginning. Does anybody remember? Yeah. It was a score minus the mean. Okay? So SS total in this context is all the scores minus the grand mean. It's all the scores minus the grand mean. So you get this overall measure of variability, the sum of squares total. That can be broken up into 2 components. They add up. a sum of squares, bless you, sum of squares between, which is actually the step before a mean square between, and a sum of squares within. I should just say an overall bless you to everybody. Right? And an SS within, which again is the step before a mean square within. But the whole point is that SS between and SS within add up to SS total. They add up to SS total. All right? So let us also, by the way, there are also less rounding errors when you do this. It also is referred to as the raw score formula. And there are less rounding errors because you're using the raw scores. But these formulas don't look like they bear any resemblance to what it is we were actually doing before. That's the nice thing about doing those mean square formulas. It was pretty clear what was going on. These sum of squares formulas are a little more obscure. Yeah? Yeah. SS total. Right, if you take each score minus the grand mean, square it and add it up. Right, like any regular sum of squares. Okay? So here are the formulas for this sum of squares approach. Now, again, you know all of these things, but here we introduce t. So this big T sub I means the total for each group. The total for each group, or the sum of x for each group. And T sub t just means the sum of x added together for all the groups. Okay, so what we're going to do is we're going to analyze the example we just did, but we're going to use these formulas. So we already know how this is going to come out, but this will give us a certain advantage. I can show you the next thing will be different. Okay, let's calculate SS within. We'll do SS within first. You know what the sum of x squared is, right? Each score squared added up. In this example, I did not give you the raw scores, but I did give you the summary statistic of the sum of x squared. So you need one or the other. So in this example, what was it? It was 842 minus, now we have to do this term. So what is this term? That is simply this, right? 48 squared, right? That's the t for the first group, divided by the n for that group. Okay, you all see where these numbers are coming from? Okay, so now, right, so that's the sum of squares. I'm going to I'll show you how to put this together, but let's calculate all the sum of squares first. That's the sum of squares within. All right, now let's calculate the sum of squares between. This term should look familiar. What is that first term? We just calculated it in the formula before. Yeah, we just calculated it before. Sometimes it's useful to do it again, but Okay? Okay? Now, so the last one we're going to do is this total. Okay. Now notice something. SS total equals SS between plus SS within, or SS within plus SS between, however we want to do it. They equal each other. And even if you looked at the formulas, they could equal each other. This is good, by the way, if you're checking things out to make sure you're doing things correctly, is, you know, adding things up and checking that stuff all together. Okay? It's a good check. Now, what I'm going to show you is, and you actually have it on either the next page or the page after, but I'm going to write it. Actually, I guess I'll write it here, just so you see where everything is coming from. And this is called an Anova summary table. An Anova summary table. It's a good way of putting your work in a table so you keep it organized and you can do the rest of the computations. So the first column is something called source. And that is the source of the variability. The source of the variability. So we have between, within, and total. So let's fill in our sum of squares, because we just did that. We can also fill in our degrees of freedom. Okay? What are our degrees of freedom for between? We did this before. Degrees of freedom between 2. What about within? 11. Now, the degrees of freedom total, we had a formula in the very beginning. It's always NT minus 1. Again, this is like a good one to remember. NT minus 1. The total number of observations minus 1. So in this example, what will that be? 13. Notice the degrees of freedom also add up. So the sum of squares add up, the degrees of freedom also add up. The mean squares don't, but the sum of squares do. Now, if I was going to fill in this table, how would I get the mean square for between? Well, again, how do I get a mean square? How do I get a variance? It's a sum of squares divided by degrees of freedom. You just divide across. Divide across, right? So it would be 9.29 divided by 2, which equals whatever that equals. Right? This is what we had before. And then within would be 29.5 divided by 11. Those are your two mean squares. Yeah? Because the degrees of freedom are NT minus K. So NT is our total number of observations is 14. Minus K, the number of groups is 3. All right? And then how do I get my F? Well, it's the ratio of those two numbers, right? These two mean squares. So it's really easy once you start filling in an ANOVA summary table, and this is what you're going to see on exams and things like that, is that you fill in the summary table. So if you get your sum of squares or your degrees of freedom, you just work your way across. And it's very simple and it's very organized. Now what if you were using the mean square formulas, right? So you put your mean squares in there. How would I fill in the rest of the table? How would I get my sum of squares? You multiply, right? So if I'm going in this direction, I divide by degrees of freedom. If I'm going in this direction, I multiply by degrees of freedom. That's why I said from the beginning of the semester, you need to know that a variance is sum of squares divided by degrees of freedom, because this stuff plays out all semester. Okay? Right, so our answer was the same as before, but these summary tables are really useful things to do. Okay. So we learned this hypothesis test. Now we have to talk about the assumptions. The assumptions. Some of these we know, right? Independent random sampling, our favorite. If you have pre-existing populations, like if you were looking at the departments in job satisfaction, or if you're looking at years in college, right? Freshman, sophomore, junior, senior. Those are pre-existing groups, right? So if you have pre-existing groups, then it's best if you can randomly sample, right? Sometimes happens, sometimes not. What if you don't have pre-existing groups? Then you have one convenience sample and you randomly assign them to the groups. Like in our therapy example, we could take our group of phobics and randomly assign them to the therapy type, in theory. Okay? For this design, we have independence of subjects across groups. Right? These people are not related to each other in any way. Chapter 15 will talk about what if the people are related, but not in this design. This design is independent. Normal distributions, all right? ANOVA is what we call robust, meaning that if we have violations of normality, it doesn't affect ANOVA quite so much. It's robust, all right? Especially if you have large sample sizes, it's usually not a problem. If you have small sample size, and if it's pretty non-normal, then you would look for a non-parametric analog to this. Okay, again, you always have to look at these things before you decide on the test you're using. Homogeneity of variance, right? We've talked about this before. We're going to talk a little bit more about this. Within ANOVA, we say generally if no sample variance is more than 4 times as large as another, and one sample size is no more than 1.5 times another, generally we say we're okay with the variances. Again, it's a pretty robust test, so it's not worried about so much. Okay, so let's talk about testing homogeneity of variance for a little bit. We talked about this when we were in Chapter 7, and I said we'd talk more about it in Chapter 12. Well, guess what? Now we're in Chapter 12. The benefit of being in Chapter 12 is like, just think, we only have 13, 14, 15, 4 more chapters. So that's good. All right, so testing homogeneity of variance. First, we're going to talk about the 2-group case, when you have 2 groups. And then we'll talk about what if you have more than 2 groups. And I mentioned Levine's test, but what I'm going to talk about here is an F-test for homogeneity of variance. An F-test for homogeneity of variance. If you remember, does anybody remember what was the hypothesis for testing homogeneity of variance? The variances are equal, right? Yeah. Right? Those variances are equal. That was the hypothesis we were testing. So now we have a really simple way to test whether they're equal or not. And it's simply this little test. It's just a really fast, easy F-test for testing homogeneity of variance. All you're doing is taking your two variances and putting them in a ratio. That's it. You always, for this test, you put the larger one on top because the table in the back of the book is set up so that it has to be larger than 1. That's the only reason why you do it that way. It's just because of the way the table is set up. Okay? So, by the way, this is the only time you would use the table for 0.025. For 0.025. Because this test is actually 1 or 2 tailed. All right? So let's actually do a really quick example. So I can show you just in general how this looks. We don't really use this, but it's a good idea just to see it. These are my two variances. Whoops. These are my two variances, 140 and 320. So we're testing to see whether they are the same or not. Okay, so the F critical value, the question is, what degrees of freedom do I use for this? So again, think back. This variance, the first variance, how did I get the variance? If I had sum of squares, how did I get the variance? I divided by degrees of freedom. What would have been the degrees of freedom for this one variance? N minus 1. N minus 1. So the degrees of freedom for the numerator here, well, for both of them, is going to be n minus 1 for each one. So for the numerator is 30, and for the denominator is 40. Those are my degrees of freedom. So what would my decision be here? Would I reject or would I fail to reject? I'd reject, which means what? Are the variances the same or are they different? They are different. That would mean, in this case, you do not have homogeneity of variance. Okay? Questions on where any of this came from, or it's like a really simple little test. However, there are drawbacks with this test. Okay? The problem with this test is that it's not robust. It is not robust. Anova is robust. This is not robust. So, if you don't have homogeneity of variance, if you don't have normal distributions, your results are not going to be accurate. Your results are not going to be accurate. We don't usually do this. We don't usually do this test. There are other tests that are better. But it's a really fast, easy way to understand how you could test for homogeneity of variance. So that's the two-group case. If you have two variances, this is how you could test it. Like I said, we don't often, but you could. What if you have more than two? The multi-group case, Then you could just do something called Hartley's F max. What is Hartley's F max? It's the same thing I just did. But if you have a lot of variances, you just take the largest one over the smallest one. That's all. The largest one over the smallest one. So it's the same idea. It's still that ratio of variances, but you're just taking the largest one of the group and the smallest one of the group. Okay? But it has the same problem as the other test. Robustness issues. So we usually don't use these tests. What do we usually do? Levine's test. Levine's test, which we've been looking at since chapter 7. So if you've rejected the null hypothesis and you're saying that your data do not have homogeneity of variance, you would have to either transform your data or modify the Anova. That's really what you'd have to do. So, for this class, you're not going to do examples like that. But, for any of you who are doing any research, again, you may not know how to do it, but you would have to know, oh, we don't have homogeneity of variance, we have to fix this in some way. And then lastly, the problem with Levine's test is that if you have small sample sizes, which is very often the case, you have low power. Okay, this is chapter 8, right? If I have low power, does that mean I'm likely to reject or I'm likely not to reject? If my power is low, yeah, likely not to reject, right? Okay, so think of it in the context of this particular thing. I have small sample sizes, which means I don't have very much power. I'm testing homogeneity of variance, and I find I failed to reject. Oh well, I guess my variances are the same. That's like working in your favor, but it's not necessarily true. It might be just because you have bad power. All right? So these are the kind of things you have to take into account when you're doing this. That's why it says, so use your judgment. Okay, lastly, varieties of Innova. Of these one-way Innovas, right? One way, one factor, one independent variable. So levels could be pre-existing or created by the experimenter. So pre-existing was our job satisfaction. Created by the experimenter was the therapy type. Okay? You could also have something called the difference between fixed and random effects. I don't want you to get bogged down into this. I just want you to hear a brief explanation. This has to do with the kind of independent variable you're looking at, the kind of factor. Okay? When we choose the levels of our factor, like the levels for the factor of job satisfaction, we chose 3 different departments, but we could have chosen 10 different departments, or 20, or however many departments there are in a university, right? So how we choose that is the difference between fixed and random effects. Fixed effects means we choose levels of the factor, they're the only ones we're interested in, right? I'm only interested in a certain subset of these possibilities. Okay? I'm not interested in extrapolating to anything else. Those are called fixed effects de novo. Random effects means that you might have a much larger pool of possible levels to choose from, and you randomly select a certain number. Okay? That's a random effects de novo. For example, let's say I'm looking at different spatial frequencies in the makeup of a visual stimulus. I might randomly choose, and there are a lot of spatial frequencies, I might randomly choose a group. Typically, in psychology, we do fixed effects ANOVA, not random effects ANOVA. The difference is in how power and effect size are calculated. Those are different. The ANOVA itself is not different. So, like I said, I don't want you to get bogged down in the differences, but if you look in SPSS, you'll see it gives you options. Are these fixed effects or are they random effects? So you should have some basic idea of what's going on there. Okay? So that's useful. And then lastly, the difference, again, and this is in your factor or independent variable, the difference between a qualitative or a quantitative factor. Qualitative is categorical, nominal, right? Like departments in a university or years in college or therapy types. Those are qualitative. Quantitative, numbers. For example, let's say my independent variable is number of hours of sleep deprivation and how people do on an exam. Okay? And I see the sleep deprivation is running rampant out there today. Okay? This is the basic idea, right? If you have a quantitative independent variable, you have a choice between doing an analysis of variance or a regression analysis. Here's what will make the difference. Let's say it's hours of sleep deprivation, and let's say we have 3 levels. 8 hours of sleep deprivation, 16 hours, and 24 hours of sleep deprivation. Okay? Your data could come out like this, and this is like the number of mistakes that people made on the exam. Okay? If the means fall in a straight line, all right, can do whatever that is. If the means fall in a straight line structure, then it's probably better to do a regression analysis rather than an ANOVA, right? Because you could do an ANOVA because you have these like 3 levels here. You know, they're like 3 groups. So you could do an ANOVA or you could do a regression analysis. If the structure is linear, you're probably better off doing a regression analysis. Now, what if the data looked more like this? Let's say after a certain number of hours of sleep deprivation, you actually got better at whatever it was. You stopped thinking about it so much. Who knows? Okay? This is not a linear structure, right? In that case, regression is not going to help you. It's not going to help you. So then ANOVA might be better. Then ANOVA might be better. Again, it always comes down to, like, what's your underlying data structure? What do your results look like when you graph them? The big difference is, and again, I don't want to get too bogged down in the details of this. If you did this as an analysis, you would calculate something called SS regression. Okay? SS regression, if you have this linear structure over here, SS regression will be the same as SS between. They really would be the same. But again, if we were getting an F, we wouldn't be using SS, we'd be using MS. And to do that, we need our degrees of freedom. The degrees of freedom for ANOVA would be different from the degrees of freedom for regression. For regression, it works in your favor if you have this underlying linear data structure. Okay? That's essentially all I want to say about this, because we could go into major details, but I don't think that will be useful at this bit. Okay? Anybody have questions on any of this? Okay, I think we are finishing here then today.